Hey, good evening, Joffrey.
Evening. How are you?
Doing well, thank you. How about you?
Mm, I'm good. Okay.
All
Sorry
right.
for yesterday because the site from where I taking the service was not working.
No problem. No problem.
Okay. Now let's start this. You send me this one, right?
Yeah,
Okay.
I was brushing through the first couple examples, I think. Uh,
Okay. First, let's do something. We already know those things, but reviewing those things and then doing the questions from your whatever you have sent me. First of all, remember this one is the carbonyl group. C double bond O. And carbonyl group is present in ketone and aldehyde. It is a aldehyde if one valency of free valency of carbon is occupied by hydrogen, maybe both sides hydrogen, but at least one side hydrogen. And if this one is going to be called ketone, if both sides of the free valencies are occupied by carbon, carbon,
okay.
then it is going to be ketone. So that's the difference between aldehyde and ketone. And because aldehyde, how many free valency you see in aldehyde?
One.
One. So definitely it's going to always appear at the end or at the beginning.
Okay.
So you don't have to mention the position of the aldehyde group. It always comes at the start. Ketone never comes at the start. So you have to mention the position. But normally if it is only 3 carbon, we don't write the 2. For example, if it is 2 propanone, instead of writing 2 propanone, we just write propanone because there is no other choice for 3 carbon.
Okay.
It cannot be at 2, it cannot be at 1. It's always going to be this one. Propanone is also commonly known as acetone.
Acetone, okay.
Yeah, this is the common name of propanone. And that's a good solvent. So this is aldehyde ketone. So for aldehyde, you don't have to mention the position. For ketone. Generally, we have to do it. But if it is in case of propanone, we don't need. In case of, if it is a cyclic ketone, suppose here it is double bond O. So definitely in this case, we start the numbering from here. So suppose if I have like methyl group is here. So because the ring is 6-member cyclohexane ring and ketone is 1, 2, the methyl is 3.
Yeah.
We are going to write 3 methyl and cyclohexanone. Cyclohexanone. Ending is going to be at O and E. You remove the E and we are not mentioning the position because we already beginning the number from there. For aldehyde, you have to take the name of alkane, remove E and add Al. Make sure the A looks like A, not looks like O. And for ketone, you take the name of alkane, remove the E and add O and E. Propanone, butanone, hexanone, and so on. Is it clear?
Yes. Yes,
So
sir.
that's about how we give the naming and numbering. And let's go to this one.
Okay.
For example, the first one. I want you to do this one.
All right, so this one here, it's an aldehyde, and this carbon here is the 1. So it looks like it's a 4-carbon chain. It should be butanol.
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 You're right.
Yep.
Do I need to write 1 butanol or not?
No.
We don't.
Like you said, this aldehyde, what do they call it? A carbonyl carbon?
This is carbonyl carbon. That's
Carbonyl
right.
carbon is.
And one more thing. Let's see. Suppose if I have this one. CH2, CH2, C double bond. Now I have 2 aldehyde group, am I right?
Yeah.
So how I'm going to write this one? I don't have to mention the position because I know that it's going to be start or beginning. I am going to write butane AN, and then I'm writing di, and then writing al.
Oh, wow.
Butane dial. Okay, like this.
Wow.
Okay, and the CW, this group, aldehyde group, sometimes they also write like this. For example, CH3, CH2, and they write CHO. So this CHO cannot be alcohol. Why? Let's try by mistake. Suppose I'm writing CH2 and opening the CHO like this, taking OH.
Mm-hmm.
Why it is wrong? Because now carbon is making only 2 bonds, which is not. Carbon makes 4 bonds. So this is not the correct way to open this one. The correct way to open this one is going to be CH3, CH2, and C double bond O and H. Now look, carbon is making 4 bonds.
Yep.
4 bonds.
That makes sense.
So sometimes they write CHO. CHO is not the alcoholic group. It is aldehydic group. You look, only 1 bond is there. So 3 bonds are 2 for oxygen and 1 for hydrogen. Is clear?
Yes, sir. Yes, sir. Yep.
Okay, now let's go back. What about the next one, B?
B, we got 1, 2, 3, 4 carbons. Bromo at carbon 3. 1, 2, 3. It should be 3 dash bromo.
And without any gap, just write butane now.
No gap, okay.
No gap.
Butanol, okay.
What about this one?
This one here.
The longest chain looks here. 1, 2, 3, 4, 5. But aldehyde is here.
Yeah. Would be 2 dash ethyl.
No. Yeah, you're right. 2 dash. That's right.
2
dash ethyl.
Ethyl and 1, 2, 3, 4. Would ethyl butanol? There's no space.
Yes, 2 dash ethyl butanol.
Okay.
Even this chain is longest, but this chain has aldehyde group. So we are going to prefer the chain which has even less number of carbon but contains the functional group instead of taking the long chain.
Got it.
Okay.
Yes, sir.
Now, what about this one?
We got UPAC name for 1, 2, 3, 4, 5. Should be pentanol.
What about this?
Three, 4 dash dimethyl 1, 2, 3, 4 pentanol.
Pentanol, you're right.
All right.
That's very easy.
Yeah, these knowing the naming system for the previous functional groups and all that stuff definitely helps.
Yes, because the main thing is you have learned the alkanes. If you know the alkane, you can do it easily like this one.
Yep.
Because the main name remains pentane, hexane, and so on.
Yep.
What about this?
Okay, the ketone. All right.
Ketone.
So this is this is acetone, right? But it would be propanone.
Propanol. We don't need to write 2.
And then this, let's see, there's the ketone functional group. Okay. And so 1, 2, 3, 4, 5. Would it be 3 dash methyl pentanone? No.
No, 3 dash methyl is okay. But now you have to mention the position of the ketonic group also.
You're right. 3 dash methyl dash 2 dash pentanone. Okay.
Of course, because I'm following your book, old book system.
Right.
But nowadays they write like 3 dash methyl. And they write, methyl, pentane, and then they write 2-O. This is also correct thing. So 2 pentanone is okay. Okay, what about this one, C?
Right here?
No, at the top here.
Oh, C. Okay. We have a cyclohexane ring with the double bond O. Okay, so that's carbon 1. So it'd be 2 dash methyl cyclohexanone.
So you're right.
Okay.
Okay, so you already know these things, okay? What about this one?
This one, we could go either clockwise or counterclockwise.
Yeah, it doesn't matter.
2, comma 5, 2, 3, 4, 5, 2, comma 5 dash dimethyl cyclopentanone.
Pentanone, you're right.
Okay.
Now, this one is not a question, but they are explaining this thing, so we are going to do this thing. This one, oxidation. General reaction. This is primary alcohol. This is what? Primary. Because the OH is attached with the carbon which has 2 hydrogen. So this is primary alcohol. When you oxidize primary alcohol, and the oxidizing agent, you can take either KMnO4, hot KMnO4, or potassium dichromate, or chromic acid, in sulfuric acid, doesn't matter. The thing is, it's going to start first going to oxidize in aldehyde, but it's not going to stop here. It will continue its journey and finally gives you what? Carboxylic acid with the same number of carbon atom. So if you are starting with 2 carbon, still you have 2 carbon. You have 1 ethanol, just ethanol, and now you have ethanol aldehyde, and now finally you are getting ethanoic acid, carboxylic acid.
Ethanoic acid, okay.
So when you are using the common oxidizing agent, KMnO4, potassium dichromate, chromic acid, and sulfuric acid, you will get aldehyde, but it's not going to stop. Final product is going to be carboxylic acid. This is another one, secondary alcohol. Secondary alcohol is going to oxidize with the same reagent, but it will change into ketone because both sides you have carbon, and ketone is not going to further oxidize and is going to stop here at the ketone. No reaction, further reaction. Is it clear?
Yes.
Okay. The difference in reactivity toward oxidation is the chief reason why aldehydes and ketones are classified in separate families. Like aldehydes go to the benzoic acid, like this one.
Okay.
Because it is not going to aldehyde oxidize, but the ketone do not oxidize. Further do not oxidize. That's why we do the tolerance reagent test, silver mirror test, to differentiate between aldehyde and ketone. Because aldehyde will give you silver mirror test, ketone will not give you. Okay, now this one, let's do this one. What you will get. Actually, they have to write what normally they are writing O only. Assume that just like the normal oxidizing agent. So what you will get.
Okay, draw the structural formula. All right.
This is aldehyde or ketone?
This is an aldehyde.
So it's going to oxidize or not?
So aldehyde further oxidized makes carboxylic acid. Okay, so it would be this same exact structure,
same
OH,
skeleton, right? But what will change here?
OH right here.
Yes, instead of C directly attached to H, C is going to attach with OH. What about this one?
It's a ketone, so there's no reaction.
No reaction, you're right. Now look here, read this one.
We got effectiveness of 2 common chemical reagents used to test for the presence of aldehydes. Tollens reagent and Benedict's reagent. Depends on the ease with which aldehydes are oxidized. In general, ketones fail to react with these same reagents. Tollens reagent is a mild oxidizing solution containing complex Ag plus ions. The oxidizing agent is the silver ion, which is reduced to metallic silver in the process and precipitates out.
Now look here. Suppose we have an aldehyde or ketone. We don't know. So we use this test, a Benedict test. Tollens test is called silver mirror test also.
We're
taking this complex of silver ion, aldehyde is present and is going to oxidize, and it will give you silver metal, which is deposit on the test tube like a silver mirror. This one. Suppose if it is ketone, so it's going to be no reaction. You will not get any silver mirror. And we just, by doing this test, we can differentiate between aldehyde and ketone. It's clear?
Yes.
This is another test for aldehyde ketone. because we know that aldehyde easily oxidized, ketone do not. Is a mild oxidizing agent, contains cupric ion, Cu2 positive ion.
Okay.
So we are taking this ion, Benedict reagents, blue color, this one is going to react and you will get red precipitate of cuprous oxide, this one, if it is aldehyde.
If it's
In Benedict
aldehyde.
reagent causes this alkaline solution to have a bright blue color. A positive Benedict test consists of the appearance of a colored, usually red precipitate. All aldehyde gives positive tolerance test, but only certain aldehydes and one type of easily oxidized ketone readily gives a positive Benedict. Like all aldehyde gives the tolerance test, so that's why generally we use that one. But only a few type, like the necessary structure, like in this case, an aldehyde with an adjacent carbonyl group. Aldehyde with an adjacent carbonyl group.
Oh.
This one is an aldehyde with an adjacent alcoholic group. A ketone with an adjacent alcohol group. These can only give that Benedict reaction. Okay, not all of them. So that's why the tolerance are the modes.
So out of these three, all of them can give a Benedict's reagent? Or?
All aldehydes gives a positive, but only certain aldehydes and one type of easily oxidized ketone readily give. Like these type will give you the Benedict reaction.
Okay.
If alcohol group is here, if another one is also carbonyl group, or ketone is there but OH is in the adjacent carbon, then that will give you. This is addition of hydrogen, which is also called reduction. Just like primary alcohol change into aldehyde, aldehyde goes to the carboxylic acid. In the same way, when you add hydrogen, it will change into alcohol. So look, this is aldehyde. You are adding hydrogen in the presence of catalyst platinum. What happened? The double bond break. One hydrogen goes with oxygen and one hydrogen goes with carbon, and you will get primary alcohol. What you will get?
Okay.
Primary alcohol.
So
if it is ketone, you will get secondary alcohol. This is called addition of hydrogen and also called reduction of aldehyde and ketone, reducing them.
So it's a way to reverse it.
Reverse it. Specific examples. This is like general, this is specific.
Yep.
They're taking propanol, it's going to change into propanol, 1-propanol. This is acetone, it's going to change into 2-propanol. Yeah? Because it will give you secondary alcohol.
Yep.
What about this one?
Let's see. So it's a ketone and it's addition.
First, I'm asking first question. It will give you primary alcohol or secondary alcohol?
Secondary alcohol.
Secondary alcohol. So what, can you give the IUPAC name of the product?
Yeah, it'd be 3-pentanol.
Very good.
Right.
What about this one?
Okay, we have here, this looks like, it's a aldehyde. Aldehyde functional group. Okay, and let's see. So if it's an aldehyde, it'll be primary. So it should be.
Can you write the structure of? Let me write this. I'm writing this one. Writing benzene ring. Okay. C is going to OH, and this is going to be H and H. Like this.
COH. H. Okay.
Commonly we call it benzyl alcohol. Benzyl alcohol. Benzyl is like this one. Like benzyl is this one with including CH2. And because alcohol, so we're just writing alcohol. Or we can also write, if you want, just taking one carbon methanol. So I can say like, and this one is phenyl group, C6H5. I can also say phenyl methanol. Phenyl methanol. Normally they write benzyl alcohol. I don't know what they have written in the answer. Okay, now the addition of alcohols. This is another one. Addition of alcohols.
Let's see. All right. You want me to read this one here? Aldehydes.
Yes, addition of alcohol. What about tertiary alcohol? If it is tertiary alcohol, can we add hydrogen?
No.
First of all,
Right? We can't, right?
we will not get the tertiary alcohol because either you will get primary or secondary. What about this one? The addition of
Aldehydes.
alcohols. This is aldehyde, am I right?
Aldehyde.
This is alcohol. Maybe same group or maybe different group, doesn't matter. And now what happens, the double bond is breaking, hydrogen is going there, and the OR group, which is shown in blue here, OR, is going to come here. After double bond breaking, one new bond will create here, and OR will go there. And you will get, this is called hemiacetal. Why hemiacetal? Because it says, I will show you why we call it hemiacetal. What is the ester? Ester is like this. Like a carbon, oxygen, and this one carbon. This is ether. But if it is double bond here, it is going to ester. What we call it? Ester. Hemiacetal means like one OR is, ether group is here, and also OH group is here. So like a carbon with one oxygen and radical, and the other one is alcohol is there. So we call it hemiacetal, half alcohol is there. Now in the next one, further you are adding another molecule of alcohol, and now both OR comes here, this side and this side. This is called acetal because two OR are attached with the, two ether groups are attached with the same carbon, one carbon. So this is acetal. If one ether group is there and the alcohol group is there, then hemiacetal. So the reaction do not stop, it goes until you will get acetal. This is aldehyde specific example. Acetaldehyde, common name, otherwise ethanol. You are adding methanol. The methanol, the double bond O becomes single and H comes here. Another one, OCH3 goes here, hemiacetal, intermediate. Then another molecule you are adding and it becomes acetal. Hemiacetal contain an OH group, hydrogen, and an OR group, and the same with the same carbon. To have alcohol and ether functional groups, hemiacetal has one alcohol group and acetal contain two ether group with the same carbon. This is acetal, same carbon. Okay, now I'm going here. H attach here, OCH3 OR goes here. Now this is second step. After one OH comes and one OCH3 comes. Now the another molecule goes, and now the OCH3 goes there, here. And this OH comes with H here, becomes water. Okay? This OH goes with H, becoming water, and this OCH3 again goes there with this carbon. So replacing the OH. Now, in a very similar way, ketone can react with alcohols to form hemi-ketals and ketals. For ketone, we just say ketals. Double bond is breaking, OH and OR is comes here. This is called hemi-ketal because you are getting from ketone. Another molecule you are adding, OR will come here, the OH will go with the hydrogen, and you will get this ketal. Now let's try this. Identify each of the following as a hemiacetal, hemi-ketal, acetal, or ketal.
Okay. So just by looking at this here, so OHC, and then this is, or OHR, and then OR. So it would be hemiacetal, no?
No. Why? Because for hemiacetal, your OCH3 is attached with this carbon. We also need the OH attached with this carbon, but the OH is not attached with this carbon. OH is attached with another carbon. So it is none.
Okay.
It is not a hemiacetal or acetal or ketal anything.
Okay.
It's clear? Because
Yeah.
for hemiacetal, you need the OH and R red group with the same carbon.
Okay.
What about the second one?
Okay. All right. So this looks like it would be hemiacetal, right?
You are right,
Because
hemiacetal.
OH is at this carbon, and then also the O and the R is
Mm-hmm.
attached to this. Okay. So this one here, we have OR attached to this carbon OR. So would this be... Is this acetal? No? No.
Look here in this case. Let me go back here. This is for ketals. In ketals, you have both sides radical carbon, am I right?
Yeah.
And when you will get the hemiketal like here, look, this carbon has OH, this carbon has OR radical, but this carbon has no hydrogen. It has both sides carbon, am I right?
Mm-hmm.
It has both sides?
Both sides carbon.
So it is hemiketal because OH and this one. In case of hemiacetal like here, hemiacetal, this one, you have OH and OCH3 OR radical, but this carbon has one hydrogen also, only one side radical.
Okay.
So in this case, I'm going to ask you to identify what is this.
It's not a hemiketal, right?
Yes, it's not a hemiketal. Because I don't see OH there.
Yeah, I don't. So it wouldn't be any of them.
No, it is going to be you can say ketal. Why? Of course, the groups are different, but still it is OR. This is the radical, this is the radical. Am I right? So basically the radicals are different. OR dash and OR you can say, but still they are ketal. It's clear? Why ketal? Because this carbon has both OR group, different even, but maybe the first time we are reacting with one alcohol, the another time we are reacting with another alcohol. And this one is both sides you have radical. So it's a ketal. If you have the answer, you can double check this one. But it is ketal.
Okay.
What about this one, D?
I know it's got to be a hemi. I'm just trying to think if it's... I'm just trying to think.
You're right, it is hemi, but what?
Can I just...
It's very simple. If it is hemiacetal, then the carbon which has OH and OR group has one hydrogen, at least one hydrogen.
Okay.
If both sides you have carbon, then it is ketal or hemiketal.
Okay, so this is hemiketal.
Hemiketal, you're right.
Okay.
What about the next question is they're asking, draw the structure formula for the hemiacetal and hemiketal intermediates and for the acetyl ketal products of the following reaction. Label each structure as hemiacetal, hemiketal, ketal, acetal. What about this one?
Okay. I'm going to grab the pen. All right, let's see. So A is... This looks like it's an aldehyde.
Okay. Aldehyde, yes.
Plus an alcohol. Okay.
But show in two steps because we have to write hemi and other things together.
Mm-hmm.
Okay, no problem.
Let's see. I'm trying to think here. Man, I gotta study this stuff a little bit more.
Let's now explain this thing. Okay, no problem. Look, first of all, I am making the benzene ring because I know there's no chain in it. So just going to add to it as. Now, C I am writing here. The H I am writing here. I know that double bond is going to break. And we are going to get 2 bonds with this carbon, single bond.
Okay.
This radical CH2, CH3 will come here. And H will go, this H will go, you can see, H will go here with oxygen. And this radical OCH2, CH3 will come here in the first step. Now in the second step, the same whole thing as alcohol again. And I will get again the benzene ring. And now this time, all other things are going to be same. OCH2, CH3. Okay, be careful when you are making a bond. I was making a wrong thing here. Make the bond with the oxygen, not with the carbon, okay? And now this one is going to also change into same thing. So what is this? Can you label these two?
Okay. This one here is Hemi acetal.
Hemi acetal. Why not ketal? Hemi ketal. Because there is one hydrogen here. That's why I'm saying, and also it is coming from aldehyde. Hemi acetal. What about the next one?
So it proceeds further on, and we would have acetal.
Acetal. Okay, now do the same type of thing here in the B part. Do it here, like here.
Okay.
Let's do like here and then go here.
Okay. All right. I'll be able to draw this.
But it's already written there. Why you're making a double bond? Because now your oxygen is making 3 bonds.
Yeah. Let me think here.
Okay, that's good.
Let me see. Okay, so I leave this as CH3. Okay.
Okay, so what is this?
This is a Hemi ketal.
You're right, Hemi ketal.
Okay.
Now what the next thing?
Further reduced, right?
Yes.
All right. Okay. would there be like water in here too? Like plus H2O?
Which one? Because definitely in this case, the OH will go with, and you can write water. Yes, water.
Water would also be
No,
a
no.
product.
What is this lip? This is hemiketal, you write?
Yep.
What is the next one?
And then this
Ketal,
one is
right?
ketal, yep.
Now I'm asking one question here. I am giving you this one. Mm, Suppose this is compound A. Then I'm going further. Can you give the structure of A and B?
Yep. Alright, so I'll do A first.
Hmm.
Let's see. H is going to go there. Okay, A. We have CH3 bond CH2 bonded to the carbon.
You're right.
And this is a Hemi acetal.
Hmm.
And I can proceed to B, right?
Yes.
Alright, B will be... So it's this same molecule? Or, like... Okay.
Okay. Now look here in this case.
Is that what we...
You are moving... Actually, these are not the two different things. Maybe I didn't... Actually, you are going from here to here direct.
Okay.
Okay.
So, that means...
And like after A, you are going to the B.
Okay. So, let's see. I'll use my eraser.
Let me erase this thing. Okay, that's correct now.
Does that work?
Yeah, that's right. Because the first OCH3 comes, now the OC2H5 comes. Okay. And this is ketal. Oh, acetal. Clear?
Acetal, yep.
Acetal. Okay, now read this one.
Let's see. Right over here. Some molecules contain both an OH and a C double bond O. Group on different carbon atoms. In such cases, an intramolecular within the molecule reaction can occur, and a cyclic hemiacetal or hemiketal can be formed.
Now look this one. The this one. In this case, there is a OH group attached here with the number 5 carbon. 1, 2, 3, 4, 5. The 5 carbon, the fifth carbon has OH group. The first carbon has aldehyde group. So what happens in this case? Because the chain can bend, and what happens? The edge goes from alcohol to here, double bond breaks, and it becomes OH. H remains as it is, and now becoming OR, like a ether group is here and this one. So this become hemi, cyclic hemiacetal. This is what? Cyclic hemiacetal, because the OH alcohol and aldehyde is in the same molecule, making a cyclic ring. Is clear? Is this clear?
Yeah, I'm just reading through it. Yep. I'm just trying to make sense of what's going on right here. Cyclic hemiacetals and hemiketals are much more stable than the open chain compounds discussed earlier. In chapter 7, okay, we'll see different sugars exist. Okay, in another reaction important in carbohydrate chemistry, cyclic acetals and ketals may form from the hemi structures. As before, all reactions are reversible. Okay.
Now look here, you already got this thing, am I right? Cyclic hemiacetal. Now you are reacting with another alcohol, CH3OH. So the another alcohol, where the OCH3 will go now?
They're saying
it will replace the OH. OH will be gone with H, making water, and the OCH3 will go here.
Okay.
And you will get cyclic acetal. Is it clear?
Yeah, that's.
Now the chain is how many? 1, 2, 3, 4, 5. Now I will give you something here. Let me see for this. I am not writing in this way, okay? You have to arrange this one in this way. Actually, this is like this. I will show you. Because you are arranging in this shape to get the cyclic structure. Basically, it is like this. CH2OH, and then you have CH2, 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 and 1, 2, 3, 4, and then you have C double bond O and H. Am I right? You are bending these two, combining them like this to make cyclic. So I'm giving you here different one. I am giving you this CHOH, CH3, CH2, can you do this thing?
1, 2, 3, 4, 5, 6.
If it is forming something like, let's go here, this one. They are doing this one, this thing, and this is a reversible thing they are showing. So let's go and do the same thing here.
So I would connect this one and this one.
That's right.
And then this would be a substituent. So I'm just trying to think.
Yes, you're right.
So if I bound them, that's where I get it. Let's see. I'm just trying to visualize it in my head. If this were the CH3 substituent, Let me think. And then here's 1, 2, 3, 4, 5 carbon. But can I just take another look at that?
Yeah,
thing
you can
again?
see here.
Let's see. So,
Everything is same as it is. Only I just make a little change here.
yeah, so they had 1, 2, 3, 4, 5 carbon chain. They had an OH at the end, and they had a double bond. So then once they combine them, the OH,
This corner you have aldehyde group.
the OH
This
goes.
place you have OH group. Look here. The only
Okay.
difference is how many hydrogens are here with the
2.
fifth carbon.
There's 2.
I just removed one hydrogen and I put the CH3 as substituent. Look, it is the same thing what I did it. Instead of 2 hydrogen, I put CH3 here, right?
Yes.
So it means it's going to be CH3 here, like this. Is it clear?
Okay.
That's I did.
But
only.
I would have to have the O right there. And
You have to write OH close to this one so that O will combine here, making a 6-member ring including oxygen. And then another substituent will go here like this. It's clear? Look, make a 6-member ring. If you have a 5-member ring from here to here, what you will do, make 1 oxygen, then I'm making like a C, I'm making another one C, 1, 2, 3, 4, 1, 2, 3, 4, 5, and now this is OH. This is gift and this is CH3 is here. I gave you this thing, right?
yeah, I'm just trying to visualize
Like
it.
this. I didn't put the hydrogen.
Alright, so like this would be like 1, 2. I'm just kind of just assigning like
Okay, no problem.
number 1, 2. There's 3, right? This would be 3. Okay, this is 4. So I'm looking at this correct. 5 and 6, and that's 5 and 6, right? So did these bond together at some point? No?
Because the OH is here, am I right? Look, let's go back and see. OH. What happening? This oxygen is joining with this. And H has, why it is joining? The H has gone. H has gone here. This hydrogen is gone. Double bond breaks from the carbon group. H gone here. And now, because there is one free valency is there, oxygen is going to join here, another bond. And that's it. So look here. This hydrogen double bond is going to break. This hydrogen is going to, because it is a lone pair, not shown here, is going to invite and hydrogen will come here. Double bond is going to break. Double bond is going to break here and is going to join here with this. So this bond is going to break.
Okay.
And you will get O, C, and the OH, H is here, and this, all other things are going to be as it is, intact, as it is.
Okay. Okay.
And this CH3 is here. It's clear? Like this.
Yeah.
This clear?
Okay. Yeah. Yeah. I'm gonna definitely be doing some practice with these.
Yeah. Okay. Now let's go these things. Identify each of the following as a cyclic: hemiacetal, hemiketal, acetal, or ketal.
Okay. All right. So A That's a Hemi because I see a hydroxyl group still.
Mm.
Let's see, carbon.
You say hemiacetal or hemiketal?
Hemiketal.
Yeah, the cyclic hemiketal. Because
Cyclic
why?
hemiketal. Yep.
Because this carbon is attached with OH. This carbon is attached with one carbon here, one carbon here. There is no hydrogen here.
Okay.
So cyclic hemiketal. What about this one, B?
Cyclic ketal. Cyclic ketal.
Ketal, you're right.
Okay.
What about this one?
C. Okay, I see a H there, so it's telling me it's a acetal, and it's a cyclic. And let me think. I don't see any OH, so it's not Hemi. So it's got to be a cyclic acetal.
What about this?
Okay, I see an OH and H, so it's a cyclic hemiacetal.
H is this. You're right, because oxygen is here, OH is here. You're right.
Okay.
We have shown, okay, acetal and ketals are stable structure, but the reaction may reverse by using water and acid catalyst. So we can reverse it by using, this is acetal. If you put water and acid, you will get aldehyde and 2 molecules of alcohol. This is. Now this is specific reactions is given there. Now let's check. What about this one?
Draw the structural formulas needed to complete the following hydrolysis reactions. Okay.
Hydrolysis means the water, because water has H and OH. With one part, H will go with one, and the other will go with OH. The water will break the other molecule also. First of all, this is acetal or hemiacetal?
Looks like a acetal.
Acetal. Now let's go here back. In this case, acetal, water and H. This CH3, this thing remains intact. These two changes. One of them change into double bond O, and this CH3, CH2 will go with, one portion will go with the OH of the water, and the another portion, the whole thing, let me explain this thing to you. I am writing the water as HOH, okay? Negative and positive thing. What happens, this portion, CH3, C2, CH2, this will go with this. And this whole thing will go with this. So what you will get, 2 molecules of CH3CH2OH. Am I right? Now here you have oxygen, here everything is gone. Now you have the condition is like this, CH3, C, oxygen remains here, nothing is here, and CH3 is here. Now carbon is making how many bonds? This carbon?
3.
And carbon makes how many bonds?
4.
And 4. And oxygen makes 2 bonds, making 1. So they just make a double bond between them. It's clear?
Yep.
So now try this one in the same way.
These are the same as like this.
Yes, everything is same, looks same, to be honest, like these two. The only thing
So,
you have, this is aldehyde, not ketone.
mhm,
This was ketal, this is acetal.
okay.
But it doesn't matter, the method is going to be the same.
Okay, so let's see.
You're right. That's
Right.
correct.
Sorry for my penmanship. Okay.
No, no.
So the products on the product side would be
What is
one.
this? What is the IUPAC name of this?
Let me see. 1, 2, 3, 4 carbon. It's an aldehyde. Butanol
Butanol. What is the next one?
plus. This is ethanol. 2 moles
Ethanol.
of ethanol.
Yeah, more ethanol.
Yep.
Okay, draw a star from the product the following reaction. The same thing is here because you already have Hemi acetal. Is it Hemi acetal or Hemi ketal? I don't know. You have to tell me.
Let me see. Carbon in the center. We have 2 carbons. It is a hemi because there's. Okay, hemi ketal.
You're right.
Hemi ketal.
And now you have to react with another molecule.
Okay.
This one.
Okay.
Another alcohol. So what's going to happen now?
Just trying to think here. It should open up, right? No.
No, it's not going to open because you have a Hemi. Hemi will go to what? When you react with alcohol, it will become Hemi to full thing.
Okay. So this
Yes, you're right.
pair
This thing
would go.
and replace what? OH. And OH will go with H.
To give me the water in addition to it. Okay.
No. You add with OCH2, then CH3. Otherwise, it's going to 5 bond. Because your H is going from here. So OCH2 is going to attach, then CH3. Now it is correct. Plus water. Okay?
Yep.
What about this?
Alright, let's see. Alright, it looks like it's a keto. No, an acetal.
You're right, it's a cyclic keto. Oh, sorry, cyclic acetal, you're right.
Cyclic acetal, okay.
Mm-hmm. And
Okay.
what's happening now?
And hydrolysis, is it?
Yeah, this is hydrolysis, water and in the presence of acid. So now what happens is going to be reversed now.
Okay. So this is basically like HOH. Okay.
Let's go back a little bit, okay? Look this one. This is acetal, acetone, right? When you are doing the hydrolysis, this one portion goes completely and make like what? Alcohol. The another portion, this one, also change into alcohol, am I right?
Yes.
Also change into alcohol. This one. In this case, only this one goes, only this portion, and H comes here with this oxygen. This whole thing goes, and so now can you tell me what happens, what's going to happen here?
Okay. So if this goes.
Now I'm going to take in this case because it's difficult to take only something from here. So I'm going to take like the whole thing here.
And OH.
And now, so what happens? This will become, what will come here?
OH, hydroxide.
No, wait a minute. Sorry, I'm wrong. Take this one, only this thing. This one, only this one. And it will go where? With the OH. It will go with the OH.
Okay.
And now that this is going to break here.
And then this H goes up there. Is that right?
No. H is not going to go there. Let me show you something. Because you look here in this case, let's see it again here. In this case, what's happening in this case? This one of the, just take any one of them, going to be alcohol. The other will be completely gone, and it will become another alcohol. But in this case, it's a cyclic thing. So it is difficult for us to do that one. So what we are going to do is, we are going to take this whole thing, this portion, and make like CH2, CH2, CH3OH. Okay. Sorry, CH3, CH2, CH2OH. And this portion is going to break, and this will become double bond. This will become like I will show you. This one, the bond is going to break from here. And this will become double bond O, and H is going to be here. And the H from here will go here, this one, this thing. So one alcohol is this portion, one alcohol is this portion. Because this is like an alcohol in the same molecule. An aldehyde in the same molecule. Is it clear?
Yeah, I'm gonna have to spend more time on this stuff.
Yeah, sure. This is like actually practicing. It's just like a Lego playing, you can say. Breaking things.
Yep.
All those things. Because whenever something like cyclic, it means there is, the cyclic thing is telling you that the OH and aldehyde or ketone is on the same molecule. So what I'm doing here, this one I'm taking alcohol, which is again becoming alcohol here. And this part which is here, making aldehyde. Is clear? This portion make aldehyde or ketone, this portion make alcohol during hydrolysis. Let's see whether we have examples cyclic or not here. Hydrolysis, no. So we can do it, no problem. It's same thing like opposite, just going, if you have a confusion here, do the opposite way. Okay, let's take, because hydrolysis is opposite of that one. Suppose I'm in doubt that I'm right or wrong. So let's take this one to confirm whether I'm right or wrong. This is carbon, double bond oxygen and hydrogen. That's I did it. Now I'm reacting with, what I'm reacting with? What was there? CH3, CH2, CH2, OH, alcohol, this one. Then what happening in this case? The double bond is breaking in this case. Basically it is like, you can say it's a two-step reaction. So sorry, this one, leave it this one. First I'm doing like here. Double bond is going to break, H will go here, and this will join here. So you will get something like this, Hemi acetal or Hemi ketone. This is going to join here, and this is going to be OH. This is your Hemi acetal, am I right? Cyclic Hemi acetal.
Yeah.
Now you are doing another reaction, CH3, CH2, CH2OH, alcohol. Now what happening in this case? It is again becoming like this. This remains as it is. And this H is still there. The OH has gone and the whole thing will come here. And it will be joined like O, CH2, CH2, CH3. Is it the same thing or not? Look.
Like, I see OCH3 and then
Oh,
over
okay.
here is OCH.
No, sorry, I'm doing this one. Not this one, this one. Sorry.
This one. Okay.
I was doing this one.
Yes.
This, am I right?
Yes.
So look, because I confirmed that if I will go back, I will get the same thing.
Okay.
Is clear?
Yeah, I'm gonna spend some time on this tomorrow.
Okay, no problem. I'm going to stop here so you can practice those things, and then you will continue from here.
Yeah,
okay?
I'm hoping that I should definitely be. I'm hoping that it'll definitely click for me.
Look,
the next
these
time
two reactions are reverse of each other. If you do this thing, hydrolysis, you will this one. Here you are doing the hydrolysis. If you do the hydrolysis, you will get this. If you take this one and add the alcohol, first just do addition of this one, combine these two part, and then add another alcohol. You will get, finally there again you will get this thing.
So,
clear?
Whether like so
you can do it in one way, then go on the opposite way.
Okay.
Try in both ways. You will practice more.
Okay. Yeah, I'm gonna definitely practice these. Okay, I'll email you and reach out to you so that we can do another session.
Okay, no problem.
I'm thinking like probably this weekend for sure.
Okay.
Excuse me. Yeah, I'm gonna I'll be getting paid in like 2 days, so I'll be able
no problem. Okay.
send you payment and we'll be able to continue. And thinking on Thursday when I get to class, he's gonna hand back the first exam, so I'll take that home and I can scan it and send it over to you. And you'll be able to get an idea for how he's testing with this class so far.
Okay.
Okay.
Okay, no problem.
Thank you so much for your time, Joffrey. I appreciate it.
Okay, take care.
Take care. Have a good night.
You too. Bye.
Thank you.